Hey everyone, in this video I'm going to show you why Karnaugh maps or K-maps are much faster and cleaner than Boolean algebra. We're going to solve the same problem twice. First we're going to use Boolean algebra and then we're going to use a K-map. And you'll understand why K-maps are much more efficient, especially during exams or tests. We're going to cover product of sums versus sum of products in a K-map, how that affects the grouping if it's ones or if the grouping is zeros, and how we use don't care conditions to dramatically simplify a logic function. So let's start with an example that we're going to solve using Boolean algebra. Say we have a function f that's given by three variables that is equivalent to these four terms over here. A naught bc plus abc plus a b naught c plus a b naught c naught. Now the way to simplify this would be first to factor out the common terms. So immediately here I see that this bc is common over there, and a b naught and a b naught is common over there. So let's go ahead and factor those out. bc a naught plus a, that's common over here and here, and then a b naught, we can factor that out to get c plus c naught over here and over here. Now using our identities, we know that a naught plus a is equal to 1 and c naught plus c is also equal to 1. Therefore, this whole equation simplifies down to bc plus a b naught. Now, this method works, but it takes multiple steps and it's easy to make mistakes, especially when your logic function might be longer, more complicated, or have several terms, not just three. So to make this simpler, we can use a K-map. K-map. The first step to solving a K-map would be to identify the minterms. So the minterms are logic ones in the map. What logic ones mean is that anything that yields your function a 1, whether that may be shown in your truth table or your expression itself, that whole term would correspond to a binary value, and that binary value can be converted into a decimal value, which corresponds to where in your K-map you will see a logic 1. So we can do that using our example over here. We see that there are four terms, a naught bc plus abc plus a b naught c plus a b naught c naught. There are four terms, and each of these terms corresponds to a logic 1 for each minterm. So if we take the first one, a naught bc, we know this corresponds to three binary digits because there's three variables correspond to 0, 1, 1. We put a 0 for a naught because it's knotted, and b and c both get a logic of 1 because they are true values. We can do that for each term in our expression. So then we have a, b, c, which corresponds to 1, 1, 1. Then you have a, b naught c. This would correspond to 1, 0, 1. Lastly, we have a, b naught, c naught. This would correspond to 1, 0, 0. So the next step would be to identifying the decimal values that each of these three binary digit values hold. So to do that, we can just convert from binary into decimal. So 0, 1, 1 would correspond to 3. So this would be minterm 3. 1, 1, 1 would correspond to 7. So this would be minterm 7. 1, 0, 1 corresponds to 5. So that would be minterm 5. And finally, 1, 0, 0 will correspond to minterm 4. Using these minterms, we're going to plot ones in our three variable K-map. Once again, three variables because function f is made up of three variables, which we can clearly see in the first logic expression. So now we're going to plot it. So we're going to put one variable on one side and the other two at the top. Just like that. Now we're going to look at the possible states to draw on the outside of the K-map that each variable can hold. So one variable can only hold two possible states, which are 0 and 1. B and C is two variables, so all the possible states that it can hold would be 0, 0, 0, 1, 1, 1, and 1, 0. Now this is the correct order of placing each possible combination of what B and C can be. The idea is each one of the binary values in B and C is only changed one time. So over here, B is not changed between these two, but C has. Only one thing has changed. And then over here, C is not changed, but B has changed. That's how you know to draw your K-map. That's the correct method. Or you can just memorize this. This is common for a 3-variable K-map or two variable K-map or 4-variable K-map. So then we can start plotting our midterms. So midterms also correspond to the binary value as we saw before. So we know that 0, 0, 0 would be midterm 0, 0, 0, 1 would be midterm 1, 0, 1, 1 would correspond to midterm 3, because converting 0, 1, 1 into decimal gives us 3, and then 0, 1, 0 would be midterm 2. And we can do the whole variable came up like that, so that would be midterm 4, midterm 5, midterm 6, and midterm 7. And then we can just simplify by drawing some lines, just like that, and like that, we will. And now we know, now our K-map is made for 3 variables, 1, 2, and 3. Now we know what our logic ones also are. They correspond to M3, M7, M5, and M4. We found that by identifying the terms in our logic expression. So let's go ahead and put logic ones in those area. So M3, M4, M5, and M7 as well. Now we've put our logic ones, we can assume that there will be logic zeros everywhere else. So 0, 0, 0, 0. Now, to simplify this K-map, we're going to first start grouping our ones. So step 1, group ones. Now there's one very important rule here. You must group in powers of 2. So 2 to the power 0, 2 to the power 1, 2 to the power 2, and so forth. Meaning, you cannot group 5 ones together because 5 is not a power of 2. So, and the easiest way to group is by first grouping the largest group of ones that you can group that correspond to a power of 2. So over here, we see that there's 3 ones on this row, but 3 does not correlate to a power of 2. But we can group these together, these ones over here. So we can write F is equal to, let's start by this grouping over here, like that in yellow. We're going to look at first the A variable. Now we know that the A variable is 1, is what we care about in this row over here. And we know that between this box over here in the K-map and the next one, A is not changing. A is remaining 1. So first we can write A because it's not changing. Now between B and C, between these two squares, we know that 0 is also, B is not also changing. If this is B and this is C, B is 0 here and B is also 0 there. But C is 0 here and C is 1 over there. So C is changing, so we can ignore it. We can put a B here. However, since when we took a look at A, we knew A was 1. We were able to just write A down since it was not changing. Now for B, we know B is not changing between these two ones, but it's a 0, so therefore we must put a naught. We can also write that as B naught. Now that we've grouped one power of 2 of ones, we can write an OR sign because we're going to do a sum of products. We're grouping ones. Now we want to group our remaining ones, which are these two over here. And we can look at first A, and once again, we're grouping these two together. You can group up, down, or left to right, it doesn't matter. Or around even, you could even go around a K-map like that, if there were ones. However, we know that 2 to the power of 1 is 2, so we can group these two together. And first, we're going to look at A. Now notice between this square and this square, A is changing. A is going from 0 and A is going to 1. So we can't write A as a term, it's changing. However, between these two, B and C is not changing. They're remaining 1. Both of them are remaining 1. Nothing else is changing. We've covered all variables, so we know that the next logic expression term would be B and C. And this is equivalent to what we found over here. BC plus AB naught plus BC. They're both the same. Now, however, this may seem longer or more counterintuitive, it indeed is much faster, especially when you're dealing with 4 variables or even a 5 variable K-map, which we'll cover later on. Moving forward, we can consider another K-map. This time, it's going to be a 4 variable K-map. It's made out of the variables A, B, C, and D, and is given by the notation sigma m, which essentially means the sum of minterms 0, 2, 8, and 10. As we previously saw, these values of minterms are logic 1s in our K-map. So we can essentially say that minterms 0, 2, 8, and 10 would correlate to what value in binary in our K-map, since we know there are logic 1s here. Minterm 0 would be 0, 0, 0, 0. Minterm 2 would be 0, 0, 1, 0. Minterm 8 would be 1, 0, 0, 0. And minterm 10 would be 1, 0, 1, 0. The reason why we use 4 binary values is because there are 4 variables to consider in this K-map. So now that we know there will be logic 1s in each of these places in our K-map, we can go ahead and draw it. The first step would be to draw the outsides of the K-map. So to draw a 4 variable K-map, we know that we can have 2 variables on one side and the other 2 on the other. So we can put A and B over here and C and D over here. And then we can simply draw the outsides. And just like before, we want to consider all the possible scenarios that each of those variables can take on for the outside of the K-map. So what can A and B? What are all the possible scenarios that A and B can possibly be? Well, A and B can be 0, 0. It can be 0, 1, 1, 1, and 1, 0. Same with C and D. It can be 0, 0, 0, 1, 1, 1, and 1, 0. The reason why we go in this manner would be, well, just like before, we want to make sure between A and B and the next state, only one variable is changing at a time. Over here, we can see that only B is changing. And then from here to here, we can see that B is staying the same, but C is changing. So that's the idea that you can consider, or you can just memorize how to draw the outsides of these K-maps. Then we can draw our outlines like this. We can ignore that. And then we know that we want to put logic 1s in each of these areas. The first step we can do is by putting a logic 1 in minterm 0. So that's 0, 0, 0, 0. Where do you see 0, 0, 0, 0 in this K-map? Well, it would be right here. So you're going to put a logic 1 there. That's minterm 0. Then you can go ahead and do 0, 0, 1, 0, which is over here. Then you can do 1, 0, 0, 0, which is here. And 1, 0, 1, 0, which is here. So it would be minterm 2, minterm 8, and minterm 10. Now you know that there would be zeros everywhere else on this K map. Just keep in mind, for the sake of this example, we ignore this first row just because there's no values over here. It's just the notation of A and B. So we can ignore this whole top column. Anyway, now for the grouping. As we previously saw, we want to group the ones in our K-map for sum of products as powers of 2. Well, over here, you may say that there's 4 ones, which is the power of 2. 2 to the power of 2 is 4, but we can't group them because they're not side by side to each other. Well, here's the beauty of a K-map. The idea of a K-map is you can group each of the ones around the K-map from both sides, up and down. So if we're going around the K-map, you can notice that this one is connected to this one if you had to turn the map over or roll it, if you could visualize that. And if you do that way, these two ones can be grouped together. But if you visualize yourself folding this map the other way, you would also notice that, this one and this one are also connected to these two ones over here. That's because when you can wrap around in a K-map, you can form bigger groups of ones that make the job of simplification much easier. So we can go ahead and group all these ones despite being on different edges of our K-map together. Here's an important note. Remember, in K-maps, you can group around the corners and use the wrap around method. We're grouping around the map like this to get all the ones. Imagine you can picture yourself kind of rolling this map in order to understand this grouping. Anyway, going forward, to write our final expression of f, we can evaluate all these ones and see what is changing. We can look at a first. Well, there's a 1 here and a has changed from 0 to 1, so we can ignore that. In this one and this one, and all 4 of these actually, b is staying the same, but it's a 0, so we know that we want to put b not. Now we're going to evaluate the top row, and since this is the same grouping, we're not evaluating a different group, we do not put a plus sign, because we're still evaluating the same group. For that reason, we can look at the top variable. We can see between all 4 of these ones, C has changed, so we're going to ignore that. However, D is staying the same. In the column where there's all ones, it's 0 over here, and it's 0 over there, so we know to put D not. Therefore, our final answer would be f is equal to b naught, d naught.